Hello everyone, welcome back to my channel. Today we're going to go over this problem of fluid mechanics. So two circular cross-section water jets strike each other and merge into a single jet as shown in the figure. Determine the speed and direction theta of the resulting combined jet. Gravity is negligible. So first we have to define our control volume and what it is. So we define our control volume as such. Oops, okay, wait, hold on. Yes, we define this as our control volume. Oop, what is going on? Yeah, that's better. We define this boundary as our control volume. And yes, we wanna apply the conservation of mass equation again, which is d dt uh cv rho dv plus integral of control surface rho u relative time dot dA, and it's equal to 0. So, so basically something to know is that d dt over control volume rho dv is equal to 0 in the case of steady flow. And if you think about it, it makes sense because this gives you the mass flow rate. This gives you sorry, the the mass flow rate through the control volume. And basically, all the mass that is flowing in is flowing out, and none of it is actually accumulating inside. So basically, it means that the mass inside this area is not changing at all. Yeah. So, however, the case for this integral over the control surface is different because basically we have mass flowing inside through the control surface or perpendicular to the area of each of these places and also exiting. So this simply means that the total mass entering each of these locations must equal the mass that like comes out at this place. So since this part is equal to 0, we can plug in 0 over here. So thus, this integral must be equal to 0 by this conservation of mass equation, since it's the only thing in the equation. Yes. And what this integral means is it's basically the summation. Integral again means summation um, of all the mass flows from here, here, and here. And we have to consider the directions of the area vectors as well when doing this. But basically, it's going to equal to first considering V1. Let's consider V1 first. And we're defining the positive x direction and y-axis to be like this. So we have rho times V1 uh dot dA. So dA is going to actually point outwards. So it's the first one is actually going to be negative since the angle between u relative and which is V1 and dA, which is the face of this control volume over here. They are pointing in the opposite direction. And cosine of 180 is -1. So it's going to be negative rho V1 times dA. So dA is actually going to be pi d1 over 2 d1 over 2 squared. Yeah. And then we also have the flow from V2. Yes, it's probably evident. So that one will be equal to also negative because the vector between V2 and the area vector of the control surface is opposite direction. So we have negative times rho times V2 times pi times d2 over 2 squared. And then lastly, we have positive rho because it's positive because it's pointing outwards the v vector and it's pointing in the same direction as the vector of the control surface area, which is also pointing in the same direction. So p times v times pi times uh times some d value because we're not given the diameter of that one. So we're just going to call it d3 over 2 squared. So let's make it explicit that this portion is d3. So that equation is indeed correct. So we substitute and simplify. So we will have, since it all equals 0, all the pi's cancel out and all the over 2's cancel out as well and the rows as well. So we're actually left with uh v, yeah. So we're left with v times d3 squared is equal to v1 times d1 squared plus v2 times d2 squared. And next, what we're going to do is realize that we don't have enough equations to solve for all the known variables. We do know V1, we know VD1, we know V2 and D2, but we have two unknowns over here, which is namely the V, the velocity outside, and D3. We don't know those values, so we need another equation. And we have to think about what else is conserved in this case. We have volume conservation, which translates to mass conservation because water is incompressible. So we assume that volume is conserved and thus mass as well. Um, but we also have momentum that is conserved. And momentum conservation is given by yet another equation. So linear momentum is conserved, and linear momentum can also be applied to a control volume using a given fixed frame of reference in the x direction. So we have our equation sheet here, and basically this is the conservation of linear momentum equation. And let's see what each of these variables mean. So where does this equation come from? So this equation is the integral form of the linear momentum equation derived from the Reynolds transport theorem applied to Newton's second law. So the physical basis of Newton's second law is that for any system of fluid particles, d over dt of the system is of integrate of v times dm is that the time rate of change of linear momentum of its system equals the net external force acting on it. So converting from a system to a control volume using Reynolds transport theorem. Using the Reynolds transport theorem for any extensive property B with intensive property B equals B over M, we can derive it as such. Uh, yes. So basically, this term in the control volume, it is important to bring up. It is from a non-inertial reference frame. So we have to take into account the inertia of an object, if we're considering it from a non-inertial reference frame. And also, the external forces split into Fs, which is surface forces such as pressure and shear, and Fb, which is body forces such as gravity and etc. So the general momentum equation over here is, and that's equal to rho times v xyz times dv plus rho times v xyz times relative velocity dot dA. And this is equal to the surface forces plus the body forces minus potentially um, non-inertial terms, such as this one. And Vxyz is used to calculate it depends on what direction, what component you want to find. So for a stationary control volume, that is if the control volume is fixed and the reference frame is inertial, that is that the relative velocity is equal to v and ARF, the acceleration of the reference frame is equal to 0. Then this is the integral form of the linear momentum equation that is used in fluid mechanics. So here we have a short summary at the bottom. And this is actually the form for the stationary control volume that we will be using to solve our problem. So let's go ahead and do that. So let's number this equation 1. And our second equation comes from conservation of linear momentum. And we're going to use the form for a simplified control volume. And we're going to break it up into x and y coordinates. So first, let's do x direction. So we will have, for stationary control volume, partial derivative with respect to t, a control volume, rho times v dv plus integral of control surface rho v times v dot dA is equal to Fs plus Fb. So actually in our case, we're gonna make it more explicit by using U for velocity. And we're gonna call it certain components. So velocity in the x direction, velocity in the x direction, times, okay, this is actually relative velocity. And then we have, these are x components. So ddt of rho times ux times dv is actually equal to 0. And it is equal to zero because no mass is accumulating, but it is in steady flow. So it's equal to zero because steady flow. What about the rest? So what about this other one, which is integral of control surface of ux rho times u relative dot dA. Note that the only change really from the conservation of mass equation to the conservation of linear momentum equation is that we have the additional term of the velocity in the x direction, the x component of velocity. Other than that, everything else is pretty much the same. And this makes sense from our understanding of linear momentum, which is P equals mv. Usually in conservation of linear momentum, we have that v component. And that v component is like this component over here, and this component is like the mass component. So yes, so for this component, we will be having uh in the x direction, we have, let's see what is contributing x component. From the V1, we will not have an x component. V2 is purely x component. And finally, V has both an x and y component. So the x component for Vx is equal to V cosine theta. So this will be equal to thus, if we basically take ux out of the integral, we can rewrite it as ux times the integral of control surface rho times u relative dot dA. And we already calculated this integral from previously, which we calculated to be this equation over here. Except now we only take the x components, which is the difference over here. So basically we have V3 cosine theta times, let me see what it was. So times rho times V times pi times D3 over 2 squared. So rho times V3 times pi times D3 over 2. Wait, yeah. D3 over 2, all that squared is actually D3 squared over 4. So we write it as such. And we actually called it V. So let's keep it consistent. And then the other component will be from the V2, which is purely just X component. So we can simply add it. And all of these velocities are flowing in the right direction. That's why they're all positive. Um, so we add V2 times rho V2 pi D2 over 2 squared. This one is also just V. So rho V2 pi D2 squared over 4. And oh wait, that one is actually negative from here. And let's see. Yes, that's our conservation of linear momentum equation for the control surface. And we have this last portion over here that we have to find, which is the uh force from the surface forces and the body forces. So Are there any surface forces? We have to ask ourselves. First of all, what is a surface force? Let's review that. So basically, surface forces result from pressure or shear, and body forces result from gravity. If we go back to our problem, it says that gravity is negligible. And I guess we don't consider viscous forces here since we just assume that it is not viscous, that it is laminar flow. So this means that the surface forces, because there are no shear forces that we have to consider, is zero, and body forces, because gravity is negligible, is also zero. So this whole equation is equal to zero. And now we will substitute and simplify. Our whole equation is going to be v cosine theta times rho v times pi. Wait, hold on. Let's not make this confusing. Yeah. D3 squared over 4 plus v2 times negative rho v2 times pi times d2 squared over 4. And this is equal to 0. If we simplify this equation, certain things cancel out. For instance, the 4's cancel out, the pi's cancel out, the rho's cancel out. And we are left with v squared cosine theta d3 squared minus v2 squared d2 squared is equal to 0. This is our equation 2 in the x direction. We have to apply the same conservation of linear momentum in the y direction as well. And similarly, let's first write out our governing equations. So our governing equations, which given by our equation sheet it's basically this equation over here. And yes, this is the form that we will be using, except now we take the y components. So let's first write out the general equation. Basically, d dt of the control volume times uy rho dv plus integral of the control surface times uy times rho times u relative dot dA is equal to fs plus fb. And let me see. Yeah, so over here again, since this is steady flow or steady state, this is 0 because no mass is accumulating, and yes, so no mass is accumulating in the control volume. So the change in mass in the control volume over time, or the change in volume in the control volume over time, is actually 0. But what about the control surface? For the control surface, we have masses flowing into the control volume and out of the control volume, so it's not going to be 0. Yes, so this form is going to be equal to uy which for V2 is going to be 0, for V1 is purely y component, and for this third V is going to be Vy equals V sine theta. So for this one we have V sine theta times rho and times U relative. So U relative and everything, we found it over here because again we can factor out the Uy as we did for Ux. So we found that it's equal to rho times V pi times D3 over 2 squared. Yeah. So it's equal to V pi D3 over D3 squared over 4. And then we let me see. So that one, oh yeah, the flow is also pointing upwards over here. That's the y component is pointing upwards. So it's going to be positive. And V1 component is also pointing upwards. So it's also going to be positive. So plus V1 times rho times V1 pi times D1 squared over 4. Let me double check to see if this is correct. Um, yes, except it is. Yes, except it is negative because again of how the normal vector of the area of the surface area of the control volume is pointing in the opposite direction off to the flow. So this one is actually negative. Okay, I'm double checking my answers and they seem to be correct. Yes. And then we set this equal to 0 because again, Fs and Fb are both 0. And this equation simplifies to V3 squared. Wait, sorry, not V3, but V squared D3 squared sine theta minus V1 squared D1 squared. And it's equal to 0. This is equation 3. So let me see. We now have 3 equations. Our first equation was this one over here. V times D3 cube D3 squared equals to that. Our second equation is V squared. Uh we have V squared times cosine theta times D3 squared minus V2 squared times D2 squared equals 0. And our third one is this equation over here. So we have 3 independent equations and 3 unknowns. The 3 unknowns are V3, D3, and theta. So we have to solve the system of equations now. Let's line up these equations all together. Mm. So these are the 3 equations, the 3 independent equations. We can solve for theta by dividing by dividing equation 3 by equation 8. So in doing so, we will have that tan theta. So dividing equation 3 by equation 2, we have V2 D3 squared sine theta uh, minus V1 squared D1 squared over, yeah, over, let me see, V2 cosine theta D3 3 squared minus V2 squared times D2 squared. Or wait, sorry, that's not how you divide equations. I meant to do it like this. V2 cosine theta D3 squared, and then V2 squared D2 squared. Um, yeah, wait, actually, let's not make this confusing. So basically, what we did was we moved this one over to the right side and this one over to the right side, so it becomes positive V2 squared times D2 squared, and this one becomes positive V1 squared times D1 squared. And then after we moved it to the right side, we divided the left side equations by each other, and then we set it equal to um V1 squared D1 squared over V2 squared D2 squared. So notice that the D3's cancel out as do the V squares, and then this gives you tan theta equals to V1 squared D1 squared over V2 squared D2 squared. And these all are known variables. And the jet speed can be found by combining equation 1 and 2. So combining equation 1 and 2, we have we have that, let me see. Yes, well, what did they do here? Yeah, so basically VD3 squared minus V1D1 squared plus V2D2 squared is equal to 0 is equal to V squared cosine theta D3 squared minus V2 squared D2 squared. And we can move everything over to one side. And if we do that, we will we will have V3 D3 to the power of 4. Is it? Wait, hold on. Nope. Anyway, combining these two equations should give you V squared times V1 D1 squared plus V2 D2 squared over V times cosine theta minus V2 squared D2 squared equals 0. And thus V is equal to V2 squared D2 squared over V1 D1 squared plus V2 D2 squared times cosine theta. And now we can plug in known values. We know that V1 is equal to 10 feet per second. V2 is equal to 15 feet per second. D1 is equal to 0.1 feet. D2 is equal to 0.05 feet. So plugging all of these values in to this equation and to that equation, we have that V is equal to 8.34 feet per second, and theta is equal to 60.6 degrees. And this matches the given answer. Yes. Yes. Okay. I hope you guys enjoyed this video and that it was helpful to you in getting a better understanding of how to approach these kind of problems. Um, and I'll be posting these slides soon after. And don't hesitate to contact with me with questions. And see you next time.